today we're going to talk about mean field theory. Continue what Ido did like in the previous lecture. So just like a quick reminder. So we're going to use some stuff that we did in the lecture. So one of them is the saddle pod approximation. So let's assume we have an integral with that form. So n is some very large number. So this is one condition. And f of x have a maxima point, maximum, where x equal to x0.
To x what? x0?
Yeah, very small zero. So, yeah, sorry, let's define like that. So, for example, if f of x is equal to x squared, so x0 is equal to 0, we have like something like that. So, if n is a very large number, so what happened? Let's think about like a Gaussian type of function. If f is minus x. So we have e to minus n x squared. We have some form of Gaussian around x equals 0. So when we increase n, the Gaussian is going to be more and more narrow. So this is for like n equal 2, and then we take, I don't know, n equal 10, and so on. So what's going to happen is that when we integrate over this function, we're going to get mostly only the contribution from that point. This is going to, it's like a delta function limit. We're going to get most of the contribution from the point of x0. So the approximation say that I can take that to be approximately e to minus n if f of x0. Okay? This is it. So this is like one tool that we are going to use. And about the mean field. So you can call it like mean field theory or mean field approximation. Depends which kind of physicist you ask. So basically what it means is that we have a system with some number of particles, and all of the particles in the system interact with all of the other particles in the system. So the Hamiltonian is going to look like sum of Si and Sj, where I different than j can have interaction of particle in itself, while I and j go both from 1 to n. So we have interaction with everyone. So this is usually introduced as like a infinite dimension kind of model, like we did like 1, 2, and so that's how physicists count, like 1 to infinite. So this is like infinite dimension in the way that like if everyone interacts with everyone, so I have like if I have a one-dimensional Ising model, so each one interactive, like only the particles next to it, so like two particles. If I have two-dimensional particles, two-dimensional system, I interact with like the, so I have something like that. So I interaction with those four particles, and when I increase the dimension, I interact with more and more particles at the same time. So basically, when it gets to dimension infinite, I'm going to have that. So it's usually like approximation that people use because we often cannot actually solve the Ising model Hamiltonian, but like for us, this is just like we start from that Hamiltonian as an assumption. So okay, so this is the mean-field Hamiltonian, and usually what we're going to do is we're going to rewrite that, because this is still not something that's very easy to work with. So we're going to rewrite that as the sum so we have sum over I of all Si and sum over J of all Sj minus sum of Si squared. So this is basically like saying this is sum over all I that are different than J. So I can write it as all I and J, and then take out the cases of I equal to J, which is just Si squared. So this is completely equivalent. So what usually happens is that we're going to have, in like normal Ising model type of question, Si is like plus minus 1. And then that expression over here, because Si squared always going to be 1, so this is just going to be n. And because it's just a constant, we don't really care about it, because the energy can always be defined up to a constant, so we're just going to ignore it. And then we're only going to be left with this one. So this is like sum of Si squared. And we're going to see in a minute what we can do with it. So this is basically the general concept, and now we're going to solve two questions from previous years, one from 2019 and one from 2015. So.
אנחנו פשוט מכניסים את החצי לתוך ה-J פה לצורך העניין, כדי שיכולים לספור את האינטראקציה פעמיים.
Yeah, like everything defined up to a constant. So I think I didn't write, but I think it's question 1. I'm not sure. Okay, so we have a given Hamiltonian minus J over N Si J, and also some external magnetic field. But now the question says that Si can be equal to either plus minus 1 or plus minus 2.
זה עדיין מודל אייזינג? זה עדיין מודל אייזינג?
It's kind of Ising model. So now, when we're going to rewrite the Hamiltonian, we do the same thing that we did here. We have minus J over, let's add the factor half, so 2n. So sum over I si square minus sum of si square. But now we have a problem because we cannot ignore this term now because si can be equal, like si square can be equal either 1 or 4. So this is no longer a constant, so we have to keep it. And it doesn't change much through the question from like difficulty point of view, but it's just important to see that like don't do like autopilot when you solve stuff like that in the test, because sometimes you have like small changes that like force you to go through like, you know, all the way. So I usually offer to do that. Okay, so this is the Hamiltonian.
But still a constant in this I squared. Still a constant, just another constant.
No, this is what I said, because si squared can be equal either to 1 or to 4. So that's depend on the state of the spin. And I don't know how many spins are in 1 or 2 states.
Okay.
So we cannot ignore it now. So I'll just write the question. So the question just say find the free energy. So we will remember what we're trying to do. Yeah.
את יכולה להסביר מההתחלה בבקשה את ה-B?
That's it? Okay. So that summation is basically, we can write it like that, like so y smaller than j or I bigger than j. So this
Not two. Not two. It's given.
yeah, this is given as part of the
Okay.
question. So I can rewrite that summation as summation over I is I and summation over j is j, but this is different than I.
אבל אז איך I קטן מ-J מתאים? אתה יוצא חצי חוץ.
So
No, that's different here. Minus. Want to do the minus si squared?
yeah, just a second. Is that okay? This is the same. This
Okay,
is summation of
yes.
two variables. It's
Yes.
just not the right way. So I say, okay, I can rewrite that as some summation of I, si, and summation over j, sj,
Okay.
for all I and j, and minus the summation of technically I, where I equal to j, so this is just I, of si squared, because it's like si, si. So this is equal to that.
Why?
Because here I sum over all I and j, except the ones that are equal to each other. And here I sum over all I and j, minus the case where I equal to j.
אוקיי. כאילו את מחסרת את מה ששונה מבעצם.
Exactly.
של, אוקיי.
Okay? So this is our Hamiltonian now. So we need to find the free energy. So what we want to use is the partition function, because that's what we know how to do. So the partition function is defined as the trace of E minus beta H, where H is Hamiltonian, and beta is 1 over T, or 1 over KBT, depends on your choice of units. Okay, so let's put in the Hamiltonian. So this is trace of exponents of beta j over 2n, sum of si square minus beta j over 2n, sum of si square, plus beta h sum of si.
Can you explain why למה כפלת בחצי?
Because here I have some of like I have interaction with 1 and 2 and 1 and 3, but I don't need to recount interaction with 2 to 1. So this one like only count every interaction once, and here I supposedly count every interaction twice. So I need to divide by half. So this is actually that. Okay, so for this part and this part, we know how to calculate the trace, because all we need to do is to count over all of the possible configuration of the spin. So we did it before, but for the sum of si squared, this is something that we don't know how to do, because we actually have two summations here. So this is a bit more complicated. So what we want to do is we want to get rid of the uncomfortable term. So what we are going to do is to use something called Hubbard-Stratonovich transformation, or how Ido like to call it, Hubbard-Stratonovich trick for some reason. So this is Hubbard-Stratonovich. So, so if you look at Gaussian integral, just because, no context. So we know that the integration of e2 minus x squared over 2 plus bc dx plus c, this is equal to e minus to e b squared over 2 plus c. This is like a known integral. So if you compare what we have on the right hand side of the equation, this is kind of look like that, right? We have something something square that on the left hand side of the equation is not something square. So what we can do is we can define b squared over 2 as that guy, which is beta j sum of si squared, and we can define c as basically everything else we have here. And now we can rewrite the partition function as a trace of an integral of, okay, so dx over square root of 2 pi, and then exponent minus x squared over 2, and then plus b. So, okay, maybe I write it here because I don't see it.
Understand what you're doing.
Yeah, I will rewrite it there because I don't have enough space.
Okay.
So if we define B from here, so B is equal to the square of beta j over n, sum over Si. And then plus C, which is just everything else that we have left here. Okay.
אנחנו מציבים כאילו במקום מקדמים את מה ש...
Yes.
ב-X אנחנו לא מציבים.
So we have expression with the sum of Si squared, and we want to write something that only have the sum over Si instead of sum over S squared. So we use that known integral and we say, okay, let's say that B is proportional to that parameter. So if I write that as this integration, so I get something that's proportional to B instead of to B squared. So which is what I want. So if I add this integration here, I get, you see that now I only have something that depends on the sum of Si.
But
or Si squared.
how you choose which term B or C?
So I choose for C everything that's like, I'm already fine with the way it looks. So like this part is okay. I know how to solve this. The part that I want to get rid of is that. So I'm going to choose that to be B squared because this is the part that's going to transform actually. Okay?
זאת אומרת לטרנספורם, זאת אומרת שזה פשוט נצמח לנוסחה, נכון? שבאמת תשאר בנוסחה ואת יכולה להשתמש בזה. נכון, טליה?
So, okay, so now if you remember where we talked about the saddle point approximation, we kind of had something that started to look similar like that, right? We had an integration and we had an exponent of a function. So what we want to do is to bring that function to look like something that I can use the saddle point approximation. So I want to make this thing look like e to minus n f of x. So I want to have something that's multiplied by n. You technically don't have to do that like when you actually go through the solution, but just to make it look more clear, we're going to go through all of the steps. So what we're going to do is just change of variables. So let's define y that's equal to x over square root of 2nj beta. So now when I rewrite the partition function, I'm going to have trace. So the dx going to become into dy, which is going to take out some factor, but we don't care about factors, so I'm not going to write it. So we have something here. So we have an integral over dy, exponents of. So now we're going to have minus nj beta y squared plus beta j sorry, this has to be with factor of half plus beta j y sum over si, and then everything else stays the same because it doesn't depend on x.
זה לא יכול יכול להיות עם פקטור 2.
Just a second. Sorry?
זה לא יכול להיות עם פקטור 2. כי פה זה הרי b חלקי 2.
Yeah, right. This cancels out. So where is this? Yeah, I had a missing factor of 2 at some point. Okay, yeah, I supposed to have factor of 2 somewhere in the way, so we're just going to
בריבוע רצית שיהיה שווה שידע בהתחלה. b חלקי 2.
Yeah, but this, like the factor of 2 cancel out here. That's why I don't have it there. But I'm supposed to have another one. Okay, let's ignore it for one. When I upload the tutorial to the model, I'll fix it. So let's just use that. Okay, so everything we did is a change of variables, nothing crazy.
How will you choose y and how change the variables?
So okay, so basically you don't have to choose it so specifically,
זה תמיד ככה?
but it's usually going to be something like that. The thing that we care the most about is n, because we want to get because we want to get to something of that form,
Okay.
so we can use the Salad approximation. So you see that like this is what I got here in the first order. We're going to discuss what happened what's going to happen here, but in the first order this is what's going to happen. So we can define it a bit differently, and eventually everything going to like organize itself, but
but how you find the y? I don't understand. It's not important, or
sorry?
how you find y? Why y equal to x divided by?
This is just change of variables. I didn't do anything. I just rewrite the integral in a different way. This is reference.
כן, אפשר להפריד?
So if I have an integral of dx f of x, I can always make it into integral of dy fy. Right? I can find y any way I want,
Okay.
and then like I'm only going to have the factor from the. So here I'm going to have like the x going to be 2nj beta dy. So I have this factor here, I'm just ignoring it because we don't care about factors. And that's it, it's the same integral. Okay, so now we want to do 2 things, which is one is to find the trace, and the other is to find the solution of the integral. So first of all, we want to find the trace, because the whole reason we wrote this integral is so we can find the trace. If we solve the integral first, we go back to where we were before. So maybe I change color. So we want to find So we have trace of exponents. So we only take the parts that depend on SI, because this is just a function. We can take it out of the trace. So we're going to have So beta j y plus beta h sum over si, just put everything together, minus beta j over 2n sum over si squared. So this is what I want to find. This is not equal to anything about it. So how am I going to do that? So we want to sum over all the configuration of the spin. So we know Si can be equal, we have 4 options for the value of Si. And over all the configurations of I. So we know that I go from 1 to n. So the summation in the integral is going to be a product. So this is equal to product of I go from 1 to n. Sum of Si is equal to either plus minus 1 or plus minus 2 of basically everything that we want here. So beta jy, beta h, si minus beta j to n si squared.
אבל אחד בעצם לא בין סכימה למכפלה. טרייס מחייב אותנו לעשות סכימה ואקספוננט יש פה מכפלה.
Yeah, but you have the traces is not exactly that. It's like over all the different configurations, like inside the.
הסכימה זה הטרייס, המכפלה זה בעצם המכפלת אקספוננט, הסכום הזה בתוך האקספוננט עצמו.
Yeah. So now you can also see why we couldn't keep the sum of s squared, because it should give us like we just cannot do that. So okay, so let's rewrite that. So we have the product of. So for si, equal plus minus 1, the si square is going to be the same. So we take this first. So it's e minus beta j over 2n. This is for that. So this multiply e to beta jy plus beta h plus e to minus beta jy minus beta h. So this is for si equal plus minus 1. Now, for plus minus 2, we have e to minus beta j over 2n multiplied by 4 for si squared. E for 2 beta jy plus beta h. Beta h, e2 minus 2 beta jy minus 2 beta h.
How you get this step?
So you have 4 terms for each one of those options. I just took out that one because it's the same for plus minus 1, so I just skip the step. Okay. So this is a cosine function. So e to minus beta j to n to what is cosine? Which constant?
כשזה פשוט SI שווה 1, אז כאילו הזמן שזה פשוט יצא כקבוע החוצה, וכשזה של 2 אז יצא קבוע 4 או משהו. זה הנקודה שלנו.
I'm not ignoring anything. This is equal.
זה כאן, שזה יוצא קבוע אחר כך שם, ושם כשני אקספוננטים שמכפילה בהם.
Yeah. So And second, there are a lot of stuff here. It's a bit confused. Yeah.
Can you explain again how you get this phi and sigma?
That from that. So this is, I think we did it a bit more elaborated in like previous tutorials when we talked about ensembles. So think about that like you have n particles, and each one of them can be in like some number of states, and you want to because the partition function comes from probability, so you want to multiply for each particle all of the possible options for the system. So you have like, okay, I have one configuration, and then I have another configuration, and then I have another configuration, and then like for each one. So
Okay. And why you choose a sigma si plus minus 1 plus minus 2?
oh, that was given in the question.
Ah, okay.
We erased it like half an hour ago. So okay, so now we have product from 1 to n of that expression. So we see that everything we have here does not depend on I. So we can just take everything here and take it and raise it to the power of n. So this is just going to be equal. Okay, I don't want to rewrite it again. So this is just equal to that. Okay, you multiply n times the same thing.
You can
I had a product from 1 to n of that.
okay.
But you have nothing here depends specifically on I. So if I multiply n times that expression, it just the expression to the power of n. Okay, so that was the trace. Now we can take that and put it back in the partition function. So
But how you get initial trace, or it's the form of you?
So I have that's the partition function that we got.
Okay.
So I want to take the trace of everything that we need to take trace of. So the first element does not depend on SI, so I ignore it for now. So I only have those. Everything inside the exponent, of course. So I just take that trace. Now I'm going to put it back.
זה איזשהו משוואה כאילו שיש לה איזשהו מבנה קבוע כאילו?
No, I just didn't want to rewrite all of the partition function. So I just took the part that needed to be traced.
Why you know that it's the form that you need for this trace?
Okay, I have trace
Okay.
of everything here.
Okay.
How would you do that?
Okay. I don't know.
So first of all, I can replace between the integration and the trace because they have nothing to do with each other.
Okay.
So I have trace of that exponent.
Okay.
So this is basically here, except of that term, because that doesn't going to be affected by the trace. So for now I ignore it.
Ah,
But
okay.
it's just that.
Why it's not affecting the trace?
Because it doesn't depend on the spin.
Okay.
Okay, so let's call everything here like what we got from the trace. Let's call it like I don't know, T. Okay, let's call it just F for a second. Okay, because I don't want you to keep recopy it every time. So if we put it back in the partition function, what we get so we have an integration of dy e to minus n j beta y squared, because we said that this doesn't change. And then this is multiplied by the trace of that. So all of that just multiplied by f, basically. So f is like, let's call it f of y because it's a function of y. But this is not what we want. We want something, we want everything to be in the exponent, so we can use the standard point approximation thing that we so like. So we want to bring that inside the exponent. So how are we going to do that? F of y. Because this is just multiplied in the exactly. So we have e to minus n j beta y squared plus ln of f y. That's it.
איפה הגענו אבל לאקספוננט של מינוס n j בטה y בריבוע? זה הקבוע שזה משם.
It's the only part that doesn't depend on the space.
Again, how do you write this ln?
Instead of multiply the exponent, I want it to be in the exponent because I want. So I just take like exponent of ln. It just.
So now it's in the exponent.
Okay, and now we can finally use the standard point approximation. Yeah. So, said the approximation said that, sorry, that if I have a function of that form, I can say that this equal approximately to e minus n f of x 0. Well, x0 is something at that point. We don't say anything specific. So that means that the partition function is approximately equal to minus n exponent of minus n j beta y0 well plus ln f of y0.
But fx לא כולל את הלן, כי הוא לא נשמע.
Yeah, so we will see. This is because I didn't write it explicitly, but we will see how it does.
Okay.
So, okay, I need to erase something.
איזה שלב עשינו את ה-e בחזקת מינוס n j בטה y בריבוע החוצה? כבר שם אחרי זה שימו.
Before we took the trace. Okay, so what is ln of f of y? So f of y is basically a very ugly expression to the power of n. So if I take the log of that, it will be n multiplied by log of a very ugly expression, right? If all of that is equal to g to the power of n, so the ln of g to the power of n is equal to n ln of g. Right? Remember logarithmic stuff. So you see that we have n now that multiplies some function. So this really is satisfied the condition that we need for the standard approximation. So now let's just write.
Yeah. Thank you.
So now let's just write everything together. partition function, but the question asked us about the free energy. So how do you find the free energy? So yeah, so there is the formula for the free energy is also F. So you write your free energy. So you're not confused with the rest of the F. So the free energy is defined by -1 over beta n ln of z.
Do that.
So if we look at the general form of z, which is basically that, so we can rewrite that as -1 over beta n, and then the ln of this exponent, so this is just going to be n f of x0. So overall, the free energy is 1 over beta f of x0. Well, f is, as we defined here, it's everything that we have inside the exponent of the z.
רגע, אז הלן כאילו נופל, כי את עושה לן של לן?
No, I take ln of the exponent. I'm still going to have this one.
Okay.
So everything here, this is for z that's equal a minus n f of y0. So I change it to y. Well, it's that. I just don't want to copy that again.
Okay.
So it's everything that's inside this at all.
Okay.
אז זה לא אותו F שהיה לנו פה, זה...
No, that's why I wrote free energy. It's a different F. We have a lot of F. It wasn't a good choice, but yeah.
איפה הסוגריים של האקספוננט נסגרו?
Okay, so here, this is, yeah, I have an additional one here.
Okay,
So everything here is inside the exponent, so all of that is f of y.
אוקיי, והשתיים קוסינוס היפרבולי הוא באותו גובה של המעריך של האקספוננט, או שהוא לא בגובה של המעריך של האקספוננט?
I just write them. So there will not be any confusion, just a second. I just write the free energy overall is equal to jy0 square minus 1 over beta ln e minus beta j n beta j y beta h plus
cos h.
Yeah, I think I'm a bit out of the screen, but yeah. So this is a good reason why we have notes. So you can just take a look later in the notes
And how you get this NFX?
So this, wait, sorry, this is y0 here. Sorry.
How we get this equation NFX from ln? I don't understand.
Which one?
In purple, ln z is equal to NFX0.
So if z is, so this is given, this is like a normal formula, and I claim that z is of that form. So if I take the ln of that, I'm only going to be left with that. So this is just like a
את מוציאה את החזקה הפוזיטיבית של E, אקספוננט, באמצעות לן. לן אקספוננט מבטל את האקספוננט.
Okay, so we find the partition, the free energy. That was fun, right? And so I'm not going to repeat this derivation, but what you saw in the lecture I hope. So this free energy is still function of y0, and we didn't say what y0 is. So what you can show, and you did show, is that y0 is actually what's called the order parameter, which is m. So it's like average magnetization. It's defined like the average of the spin SI. So this is called the order parameter. So we're going to, so the reason it's called the order parameter, we will talk about it later when we talk about like everything that we did in the context of phase transition. But for now, it's just a parameter, just a name. So instead of y0, you write m. It's like a given thing.
לא הבנתי, זה סיימת את התרגול או שזה המשך?
We finished. I just say like this is still function of y0, so I just tell you what y0 is. This is from lecture.
ואיך ידעת שזה אמרתי שזה באמת מה שעושים בהרצאות, מה שהנפתר כוואי.
Because it's always, it's like by definition. Okay, so that was one question. And before I move to the next one, which is a bit less exhausting, tiny little bit less, questions about everything we did.
The question about this מעבר, how איך הסרת את האינטגרל הזה? למה אפשר להגיד שאפשר להוריד אותו?
So, I explained at the beginning of the tutorial. So this is also something that I think you talk more elaborated in the lecture. So I'm not going to prove it, but it's basically if you have a function, f of x that have like a here we defined it with minus, so it's a minimum point, but all of that it's like just look like something like that, where the maximum is in around x0. So if n is a large number, this is going to be very narrow function. So most of the contribution going to come from the value of the function here. So you can write like f of x0 as like f of x as like a Taylor series around x0. So this is like the first term in the series. So we just ignore everything that's come out. Thinking the explicit derivation, you also have like the second one, which is going to give you like something that multiply that. I wrote it also in the notes, so you can take a look there. But like this is basically what you need to do.
לא כל כך הבנתי לגבי החלק של, כשאנחנו שמענו שלן של g בחזקת n שווה ל-n לן g וכל זה, ואמרנו את האינטגרל לממש, חישבנו את האינטגרל, כי בכלל אמרנו פחות או יותר מה זה שווה. למה אמרנו שאלו מתאימים לסוג אפרוקסימיישן שרצינו, לסדר אפרוקסימיישן? אמרנו לזה, כמו שזה בדיוק מתאים לזה, לא מתאים כך למה התקרנו שם.
I'm not sure.
אמרנו שזה כאילו מוכיח שאנחנו באמת יכולים שיש בסדר אפרוקסימיישן כשעשינו שם.
Oh, because you want something that looks like that.
כאילו, את אומרת שככה בעצם קיבלנו משהו שיהיה הכל n כפול משהו.
If you are mathematicians, and we are not, so like we don't care, but like you need to show that f of x also like behave in certain way, because if you have something like very big that multiplies something very small, it's not going to work, right? I can always divide and multiply by n, but we assume that everything behaves in the way we want it to behave. So this is like so this is like as good as we're going to do it. We're just going to write something that looks like that and you say like, yeah, that's fine.
זאת אומרת, זה בדיוק מתאים לצורה של n כפול משהו. וזה בדיוק הצורה של זה.
Okay, so next question. So we did like a full derivation here, and if you have a question like that in the test, which there's good probability that you will, because it's a pretty common question, I think. You don't have to go through all of the derivation, But as you saw in the beginning, that like we had this s squared term that like we say, oh, usually we ignore it, but like here we have more options for SI, so we cannot ignore it. So like just make sure that like everything that we usually do can also be applied here. So if you skipped steps, make sure that like it's justified. So 2015 question 3. This is so this is the given Hamiltonian. J minus H1, and now we're going to have two different terms for the field. One for the spins that go from 1 to n/2, and another one with a different field for I go from n/2 plus 1 up to n. Okay. So the question is the same as before, find the free energy. And the majority of what we're going to do is going to be basically the same, so I may skip a few steps. The spin, in that case, is only plus minus 1. So it simplifies it a little bit. And that's it, that's the question. So, okay. Find the free energy. It's always the free energy.
Question: how SI can be plus minus 1 if it's have a sigma from 1 to n divided by 2?
No, I is like for the different particles. SI is the state of each particle. So we have n particles, each one can be in one of the states.
It's
yeah,
the
it's
spin
value
of
of SI.
one particle.
Yeah.
Okay. That can be plus 1 minus 1.
So, okay, so we use the same kind of trick as we did before. So we rewrite that as sum SI square, sum of SI square. But now SI square is always going to give us 1, so we can just ignore that. This is just a number.
Why you can ignore it?
SI, either if it's equal 1 or minus or plus 1, it's SI square always going to be 1. So this summation is just n, and n is just a number. So I can always rewrite the Hamiltonian up to a constant. It's just the energy. So we don't care about that.
כאילו בגלל שזה הופך לקונסטנט, אז אפשר לא להתייחס אליו.
So the partition function is trace of E minus beta the Hamiltonian. So this is exponent of beta j s square plus beta h1 plus beta h2 and exactly like before, we're going to say that that is equal to a Gaussian integral. So this is all equal to a trace integral e minus x squared over 2 I will write it. So that's the, we spend enough time on that. So this is basically, this is exactly like we did before. The only thing that's going to change is the factor that we have here, what used to be C. So I'm just writing it after like the change of variables and all of that. So the main I don't know, point of this like exercise is the fact that like the summation of the fields term is not like as trivial as it usually is, because you have just for half of the particles you have one field and for half you have another. So the question is how are we going to treat that when we take the trace of the function? So if we have trace of so beta j y s I, so this go from 1 to n. So the summation over the state of SI is going to be the same, like not exactly the same because we have just plus minus 1, so we have something a bit simpler. But when we look at the product of all the different particles, we're going to have just two separate products, one for I for 1 to n over 2 and one for n over 2 until n. So we have one product for Si equal plus minus 1 E beta jy plus beta h1 Si multiplied by product from n over 2 of E to beta jy plus beta h2 Si. So instead of one product, we have two.
Yeah, why you?
Okay.
Why is pi n divided by 2?
Because we have two separate summations here, and we need to separate for the different cases. So one's going to be for this case, and one going to be for that case. And the first summation is for 1 to n, so we just separate into two different summations. Like it doesn't matter. It's going to appear in both products.
I'm not understanding.
So
Why it start from 1 to n divided by 2 and 4 n divided by 2 plus 1 to n?
So if we had, if h1 was equal to h2, so that's what like the normal case that we know. So you didn't have that. You just had product from 1 to n over 2. From 1 to n. So that's what we did last time. Okay.
Okay.
So but now we have so this is like a product of n different terms. But now we have two types of particles. One field H1 and the rest of the particles field H2. So the product is going to be n over 2 terms multiplied with that field, and n over 2 terms multiplied with that field. So I just separated them. Yeah.
But why you start from n to plus 1? Yes.
בסכום השני.
The same as that summation.
אוקיי. זאת אומרת, זה אחד מ-i שבין חלק ל-2 עד n במקום לשים מעל ל-1 עד n.
Yeah.
זה דבר ראשון. דבר שני, איך ה-y בריבוע, אני מבין שאנחנו רוצים אותו להפעיל את של ההרווארד וכל זה כאן, אבל כאילו אני מבין שיש פה y בריבוע, אבל כאילו איך זה הפך להיות פשוט רק חזקה 1, כאילו נשאר חזקה 2 ומשהו.
No, y squared is still here. I just didn't write. This is not equal to that. I just take the trace part. I calculate it and then I will put it back.
אתה לוקח את החלק שרלוונטי לפייס ועושה את זה שרוק, יש פה איזה קבוע שמופיע החוצה פשוט.
Yeah.
Now it's clear.
Okay, so now, so that summation going to be just 2 cosine or body cosine of beta jy plus beta h1. This is similar to before, and this is 2 cosine beta jy plus beta h2. Just the sum.
אוקיי, עוד פעם, ה-n חלקי 2 פלוס 1 זה בגלל שהאינדקס מתחיל ממנו, אבל יש לי סיגמה אחר שהוא מתחיל מ-1, כאילו, אבל זה לא משנה, כי אנחנו יכולים לבחור כל n.
Right.
לא.
This corresponds to that sum, and that one corresponds to that one, that sum. And this one appears in both because this is like writing. This is like I have sum from like I to n over 2 plus sum from n over 2 to n. I can always write that.
Okay.
So this is overall. So we have 2 cosine beta jy plus beta h1. So all of that to the power of n over 2 because of that product, and 2 cosine beta jy1 plus beta h2. All of that also to the power of n over 2. So you see that from all of the derivation, the only thing that changed is that instead of have like one thing to the power of n, we just need to separate it to the two places.
סליחה, למה בחזקה n חלקי 2 בשני?
Because between n over 2 to n, you have n over 2.
בגלל שזה מתחיל מ-n חלקי 2.
Yeah, because you already start from.
ופלוס 1
But you need to have like overall n particles.
לא צריך פלוס 1 אולי?
No, because it includes like n. So think about it like that. If h1 was equal to h2, I'm going to need like to have n in the exponent. So it's overall need to be consistent. this is the trace part, which means that the total partition function is, again, the integration of the exponent of all of that. And we're going to use, again, the Salad-Pot approximation, so we're only going to take the exponent at some point x0. So I'm going to write it after the approximation. So this is approximately exponent of minus n y0 square beta j plus. So now I have, I'm going to have log of that. So instead of taking out n, I'm going to take out n over 2, because it's like writing all of that in the power n over 2. So this is plus n over 2 ln of 4 cosine beta jy plus beta h1 multiply by cosine of beta jy 0 plus beta h2. This and it.
question. את מה שמחק, במעבר לסגול אחרי זה, זה שינוי משתנים? החלפת משתנים? כאילו
It's after change of variables, yeah.
It's after change, okay. הסגול זה אחרי שינוי.
No, the purple is just the trace. It's not all of the partition function.
אוקיי. אבל זה...
But yeah, it's after.
זה אחרי, אבל בשחור זה גם היה אחרי.
Yeah, so I wrote, so what happened is that I wrote here the first expression of the partition function just from the trace.
Okay.
And then between here to here, I said I'm doing both the Haber-Satonovich transformation and the change of variables.
Okay.
They're exactly identical to what we did before, so I don't see any point to repeat that. And then I took the trace and so on. Okay, so we do need to find the free energy. So, yeah. So everything that multiplied by y was the same. Like the only thing that changed is the field length.
How do you get this equation?
So we had the partition function here, which looked like e to n multiplied by stuff.
Okay.
And with that inside here, this is also similar to, it's the same as what we did before.
Okay. Okay.
So we get the contribution at y0, and as before, f is just basically the function inside the exponent, right? We say it's that. So it's going to be equal in our case to j y0 square minus 1 over 2 beta ln of 4 cosine basically all of that. So this and another cosine. But again, y0 is just
Here is the sum of the average of the both.
M, yeah. M is basically that. There are some methods of like mean fields where you take immediately like that, you say that this is like a constant, and then, but this is like a different approach. We don't do that.
What do you say again about the sigma SI?
This? This is the M is like the average magnetization. It's defined like that. So it's the average of the spin states. So we can also write it like that. I think in the derivation it will use that at some point. Okay, so that was the second question. So that was a bit exhausting tutorial. But you see that like the method is pretty simple. It's just a bit ugly calculations. But like yeah, you do it once and fast. Like you know how to do that.
וככה אנחנו אמורים לפסוק במבחן, ממש
So
ככה הוא מצפה.
So I'm not sure what would the like minimal thing that he wants you to do, but like you don't have to do it as we did in the first question. I do recommend to do it as we did more or less. Like you can define stuff and like just instead of copy everything, but like because you have enough time in the test, and sometimes like you see like you change stuff in the question that like change some of the stages, so you have to be like pretty careful with what you do. But like besides that, it's a mess. Okay, so good luck.
Thank you very much.